Hey y'all, welcome back to a Slice of Physics. Having discussed series resistances in the previous video, we're now going to discuss the arrangement of resistances in parallel in a circuit. First, we'll see how we can recognize this parallel arrangement. Then we will talk about the current and potential difference considerations when we have resistances in parallel, which will help us move on to what is the equivalent resistance when we have multiple resistances in parallel and want to represent them as a single resistance. And finally, we will close with how we used Kirchhoff's junction law and verified Kirchhoff's loop law in these circuits. So here's a circuit with two resistances in the parallel arrangement. Let's call these resistances R1 here at the top and R2 for the bottom one. And let's also say that the battery has an EMF or potential difference of delta VB. First, we recognize parallel resistances by one important fact, and that is that the ends of the resistances are connected together. So what we mean by that is there's an ideal wire that goes from the left end of R1 to the left end of R2, and another ideal wire that goes from the right end of R1 to the right end of R2, and so that's what makes it a parallel arrangement. And because the ends are connected by ideal wires, they are at the same potential. So the potential at this point, let's call it A, and this point B is the same. And in fact, it is the same as the potential at this point C. So VA equals VB equals VC because they're all connected by ideal wires. Similarly, on the other end, we can see that if we have this point as D, E, and F, we can see that VD equals VE equals VF. And this is because these are all connected by ideal wires. Now clearly VA is not equal to VD because there's a resistance in between, which means there'll be a potential drop. And similarly VB is not equal to VE. Again, there'll be a potential drop. But those potential drops will be the same amount because the potential on either end is the same. And that's a key point. So whenever we have resistances in parallel, the potential difference delta V is the same across all resistances. So in this case, delta V1, where delta V1 is the potential difference across R1, equals delta V2, the potential difference across R2. Now let's bring current into the picture. Let's say that the current going through R1 is I1, and the current going through R2 is I2. We can use Ohm's law to write I1 as delta V1 over R1, and I2 as delta V2 over R2. And then if we talk about the current at point C and call that IN, because that's the current coming into the junction, and it splits two ways into I1 and I2. And so from Kirchhoff's junction law, I have IN equals I1 plus I2. Now, since one of our goals is to determine the equivalent resistance of these two resistances in parallel, let's draw an equivalent circuit. So that circuit would look like this. It would be the same battery, but these two resistances in parallel would be replaced by a single equivalent resistance. So I still have delta VB over here, and I got an equivalent resistance. And if I were to talk about the current through this circuit, the current out of the battery in both these circuits has to be the same. So this I would be the same as IN for these two circuits to be equivalent. So I can write I equals IN, and that equals I1 plus I2. Now in the simple circuit, I equals the potential difference across this equivalent resistance, let's call that delta V, over R equivalent, simply by Ohm's law. And by the way, this delta V is equal to this delta V1 and delta V2. So let's note that over there. The potential difference across these 2 points is the same if this were to be an equivalent resistance to the two resistances in parallel. So that leads us to this I, which is delta V over R equivalent, equals I1, which we have here as delta V over R1. I didn't write delta V1 because it's the same as delta V, plus again delta V, instead of delta V2 I can just write delta V, they are the same, over R2. And now if I divide both sides by delta V, this will lead me to 1 over R equivalent equals 1 over R1 plus 1 over R2. And this is the form for the equivalent resistance when we have resistances in parallel. You remember in series it was just simply adding the resistances, and here we got to do a little more number gymnastics. We've got to add the reciprocal of each resistance and then take the reciprocal of that to get R equivalent. So another form of writing this, as your textbook does, is for parallel arrangements. You've got R equivalent equals 1 over R1 plus 1 over R2 plus, if we have more resistances, the same thing. And then I can raise that whole thing to minus 1 power, which is the same as the reciprocal. So when I take that, I get R equivalent. So having seen how we used the fact that the resistances in parallel have the same potential difference across them, and we used Kirchhoff's junction law, that the current splits at a junction such that the sum of the current coming in equals the sum of the current leaving the junction, we derived this form for equivalent resistance. Now let's take some numbers and see how this works out. Okay, I'm going to give you some numbers now and say that the potential difference of the battery is 9 volts. This resistance R1 is 6 ohms, and the resistance R2 is 9 ohms. We want to find out the equivalent resistance of this. We want to find out the current through each resistance and the current coming out of the battery. Okay, first let's figure out how the equivalent resistance. So I've got R equivalent equals 1 over R1 plus 1 over R2, and when I get that, I got to take the reciprocal of that whole thing, which in this case, when I put the numbers in, it's 1 over 6 plus 1 over 9 to the minus 1. You can use your calculator to do this. I'm going to just quickly do a common denominator thing. So this would be 3 over 18 plus 2 over 18 to the power of minus 1, which would be 5 over 18 to the power of minus 1. Since I have common denominators, I can add the numerators. And reciprocal is simply reversing the numerator and denominator. So this would be 18 over 5, or 3.6 ohms. So that is the equivalent resistance. And so that brings us to this circuit. So I've got 3.6 ohms here. And since I have 9 volts for the potential difference of the battery, and there's nothing else in between, I can get this current through this resistance as 9 divided by 3.6. So let me do that. So I would simply be 9 divided by 3.6, which would give me 2.5 amps. So that would be the current coming out of the battery, which in this case also here, or this I in, would be 2.5 amps. Now that current then splits into I1 and I2, and we want to determine what these are as well. Now as we analyze this circuit, we can see that the potential difference across this first resistance is the same as the potential difference of the battery, because there's just ideal wires there. So that's just 9 volts. And then R1 is 6 ohms. So my I1 would simply be 9 divided by 6, which is 1.5 amps. And similarly, I can do the current for I2. I know delta V2 is also 9 volts in this case. Potential difference across resistances in parallel is the same. And in this case, it's the same as the battery's potential difference because there are no other resistances. So then I've got 9 volts and 9 ohms, which will give me I2 as 9 volts divided by 9 ohms, which is 1.0 amps. And you can see that if I have 1.5 amps going up through this segment and 1 amp going down through this segment, the current coming in has to equal the sum of those two, which would be 2.5 amps, which is what we got when we used the equivalent resistance. So it all adds up and ties in. Now there are a couple of points that I want you to note here. When we have resistances in parallel, number one, the equivalent resistance is less than all the resistances in parallel. We see that here our resistances in parallel were 6 ohms and 9 ohms, and our equivalent resistance was less than both of those at 3.6 ohms. At first that might surprise you. We added resistances to the circuit and reduced the overall resistance of the circuit. That does not happen in series. When we add resistances in series, we add resistances to the circuit. And the way to think about that is, not only did I add a resistance to a circuit, I also added a whole new pathway in the circuit. So I added a whole new conduit for the current to flow. which increases the demand from the battery. So when you plug in your laptop to charge and you plug in your phone to charge, those two things are parallel connections in the wall. And as you plug in more devices, you're increasing the load, which means you're increasing the current from the battery or from the power station in the case of a household electric system. And so in order for the current demanded from the battery to go up, the equivalent resistance must go down per Ohm's law, because I equals delta V over R. As current goes up, resistance must go down. So that's what we see over here. The second thing you're seeing here is that for resistances in parallel, higher resistance has lower current going through it. Again, that's just a consequence of Ohm's law, but we see here that the 6 ohm resistance had a 1.5 amp current and the 9 ohm resistance only had a 1 amp current. Higher the resistance, lower the current through it when we have resistances in parallel, because the potential difference across them is the same. Lastly, let's quickly see if we can verify Kirchhoff's loop law in this case. In this circuit, I have 3 loops. I have one loop going like this, the battery and the top resistance. I have a second loop going through the battery and the bottom resistance alone, and a third loop, which is in this rectangle over here, which involves resistance 1 and resistance 2 and does not involve the battery. So in the first case, as I go in this direction, I got an increase of 9 volts, and I come over here, no change in potential, come over here, no change in potential. When I go across R1, I got a decrease of 9 volts, and then no other change. So plus 9 volts minus 9 volts leads to 0. Same thing when I go from the battery to the lower resistance. Plus 9 volts when I go across the battery, minus 9 volts when I go across R2. No other change, so that adds up to 0 as well. And finally, this third loop here, when I go in this direction, when I go from D to A, there is a potential increase. Remember, in the direction of current, potential drops across resistances, but when I go across this loop, I'm going opposite the direction of current, so I encounter a potential increase going from D to A, so that would be plus 9 volts. And then for R2, I'm going in the direction of current, so the potential is dropping by 9 volts, and the sum total of those also equals 0. So in this class of physics, we looked at resistances in parallel. We first realized that the potential difference across resistances in parallel is the same. We used that and Kirchhoff's junction law to derive an equation for the equivalent resistance when resistances are in parallel, which is a little bit more involved computation than when they are in series, which is just simply adding them. Then we realized that adding a resistance in parallel to a circuit decreases the equivalent resistance of the circuit. This R equivalent would be smaller than all of these resistances that go into the equation. And that's because adding resistances in parallel increases the overall demand of current from the battery. And so the equivalent resistance must go down by Ohm's law. And finally, in this, we recapped how we used Kirchhoff's junction law to derive this and how we verified Kirchhoff's loop law once we got all the numbers worked out for our 2 resistances in parallel. Thanks. See y'all later.